If you want to fly from New York City to Madrid, Spain, two cities that sit at almost the exact same latitude, the shortest path is not to point your plane east and just, fly straight across the Atlantic Ocean.
Right, which sounds completely wrong.
It does. To take the shortest, fastest route, a pilot actually has to point the plane northeast, flying, hundreds of miles out of the way, deep up toward Nova Scotia, before coming back down toward Spain.
Yeah, it completely breaks your brain when you look at a standard map hanging on a wall.
Right.
Because on that flat piece of paper, you're taking a massive looping detour.
Exactly. And that brings us to our mission for this deep dive. We are deconstructing the ultimate geographic magic trick, basically exposing why the flat maps we trust every single day are, well, secretly lying to us about distance, routing, and reality itself.
We've been conditioned since, elementary school to look at those classroom maps and treat them like blueprints of reality.
Yeah.
We just assume a straight horizontal line on a map translates to a straight horizontal line out there in the physical world.
And to figure out what's actually happening, we are pulling from a really fascinating stack of sources today. We have a Korean academic paper diving into the math of what they call nation-centered world maps, a set of mind-bending web visualizers by a developer named Jason Davies, and a breakdown by a YouTube channel called Best SUP Tour that actually runs the numbers on these hidden distances.
It's a great lineup.
Yeah. So, okay, let's unpack this by setting up a premise that I think trips up almost everyone.
Let's use 37 degrees north latitude.
Perfect. So you're in a city at 37 degrees north, and you want to travel to a destination on that exact same horizontal line.
Right.
Visually, intuitively, you just travel perfectly horizontally. You go straight east or straight west. Why deviate?
Because that assumption relies on a flat grid, and, well, we live on a sphere.
Right, minor detail.
Yeah, just a small thing. But to understand why the horizontal line is a trap, we have to talk about the difference between a parallel, which is just a line of latitude, and what mathematicians call a great circle.
Okay, I'm going to break this down without getting bogged down in the textbook formulas, because the academic paper goes really heavy into the geometry here.
Oh, very heavy.
So think of the Earth like a massive spherical onion.
Okay, an onion.
If you take a knife and slice it perfectly in half right through the middle along the equator, you get the biggest possible slice.
Exactly. And that equator is the only line of latitude on our planet that qualifies as a great circle.
Right.
Because its center is the exact center of the Earth. It has the maximum possible radius.
But as you move north from the equator and you keep taking horizontal slices out of that onion, the slices get smaller and smaller. The circles literally shrink.
Yeah.
So a line of latitude at 37 degrees north, or say 45 degrees north, isn't a great circle at all. Navigators call them small circles.
This is where the geometric reality just completely overrides our visual intuition. As you move away from the equator, the radius of those latitude circles is shrinking. The paper actually calculates this by taking the Earth's maximum radius and reducing it based on how far north or south you go.
Right, because the planet is tapering off toward the poles.
Exactly. And because the radius is physically smaller up there, the circumference is smaller. But a great circle, by definition, always maintains the full maximum radius of the Earth.
Got it.
It always cuts the globe into two equal hemispheres.
And the golden rule of spherical geometry is that the absolute shortest route between any 2 points on a sphere is always a great circle.
Always. Without exception.
Okay, to picture this, imagine holding a basketball. Take a piece of string and wrap it around the ball.
Okay.
Now, pin that string at 2 points near the top of the basketball, representing two cities on the same northern latitude. If you leave the string loose, it might just rest there, parallel to the floor.
Right, looking like a normal latitude line.
Exactly. But the moment you pull that string taut to find the absolute shortest distance between your two pins, the string slips.
Yeah.
It doesn't stay horizontal. It actually arches upward, slipping away from that parallel line to tighten itself around the curve of the ball.
What's fascinating here is that the slipping string on the basketball is exactly what your airplane is doing when you fly from New York to Madrid.
Oh, wow.
The plane is the string pulling taut. The shortest physical path between two cities on the exact same latitude doesn't stay horizontal.
Right.
It arches upward, aiming toward the North Pole before coming back down to the destination.
Which means if you trace that arching flight path and draw it onto a standard flat classroom map where the latitude lines are perfectly straight horizontal bars, the great circle path looks like this massive, ridiculous curve.
It looks completely wrong to our eyes.
It really does.
It looks like you're taking a scenic detour through another country.
So if the string slips upward,
Right.
how high does that arch actually go?
Well, to figure this out, we can look at the digital model built by the researchers in our academic paper.
Right, the Korean paper.
Yeah, they created this really cool web visualization tool specifically to track this curve, and they centered their math on Seoul, South Korea, which conveniently sits right at that 37 degrees north latitude.
We actually have the UI for their Vertex calculator in our sources, and it has this really cool interactive slider.
Yeah, the slider makes it so clear.
It lets you adjust something called the longitude difference.
Yeah.
Basically, you leave your starting point in Seoul, and you just slide your destination further and further away along that same latitude line.
And as you push that destination further away, the math forces the great circle to stretch.
The vertex, like the peak of that arch, just pushes higher and higher north.
Exactly. If your destination is close, the arch is subtle. But if you slide that destination halfway across the globe, the shortest path between those 2 points arches incredibly high.
Yeah, pushing way up into the northern latitudes before coming back down.
Right.
But here's where it gets really interesting, though. If we pull up the map visualizers from Jason Davies, he takes these perfect, tightening great circles on the 3D globe and mathematically flattens them out onto a 2D map.
This is where it gets crazy.
Yeah, when you flatten a sphere, a perfectly straight great circle turns into this bizarre, repeating sine wave. It literally looks like an S shape oscillating up and down across the continents.
The visual disconnect is profound. I mean, you are looking at a sine wave looping wildly across the paper, and your brain is screaming that this must be the longest possible route.
Right, because a straight line is supposed to be the fastest.
Exactly. Meanwhile, the perfectly straight horizontal latitude line on the map looks incredibly efficient.
But the straight line is the illusion.
Yes.
And to see what happens when you actually bet money on that illusion, we have to look at the YouTube video from the channel Best SUP Tour. They stopped looking at the theory and ran the numbers on real-world distance savings.
Right, and we connect this to the bigger picture. This isn't just a fun math puzzle. We are talking about global logistics here.
Oh, absolutely. Let's look at their Eurasia route example.
Okay.
They trace a path along the 45 degrees north latitude line, starting in Europe, around Austria or France, and heading to Mongolia. That is a longitude difference of roughly 59 degrees across the globe.
That's a huge distance.
Yeah. Now, if you are a pilot who trusts the flat map and you just follow that horizontal latitude line, your flight path is 8,190 kilometers.
You're right.
But if you trust the math of the sphere and take the great circle route that arches way up north, the physical distance drops to 7,413 kilometers.
That is a savings of almost 800 kilometers.
It's massive.
Think about what 800 kilometers means for a commercial airline flying a Boeing 777.
Oh, I can't even imagine.
That is thousands of gallons of jet fuel saved on a single flight.
Right.
It's a massive reduction in carbon emissions. It's an hour of flight time erased, which changes how crews are scheduled and how international airspace is managed.
Just from following the curve.
Exactly.
And the second example they ran was even more tangible, U.S. listeners. They mapped a coast-to-coast route from the east coast of the United States to the west coast.
Okay, yeah.
To find the shortest physical path, you don't fly straight across the country. You actually have to point your plane 440 kilometers further north, flying deep up into Canada.
Yeah.
You are deliberately flying hundreds of miles, quote-unquote, out of your way to the north. But doing that actually saves you 113 kilometers on the total trip length.
That is, what, 15 or 20 minutes of flight time, saved simply because the pilot is navigating a sphere?
Right.
While the passengers looking at the seatback screen think they are taking a detour.
The massive curved detour on the map is actually the straight line in reality.
We implicitly trust the flat grid because it's easier for our brains to process, even when the underlying geometry proves it false.
Wait, I have to push back here.
Okay.
If standard maps are this bad at showing distance, and they trick our eyes this completely, why don't we just draw new maps?
Oh.
Like, why not create a map where the great circles are drawn as perfectly straight lines and the latitude lines are the ones drawn as curves? The guy in the YouTube video actually suggests doing exactly that.
It's a completely logical leap, and it's actually exactly what the nation-centered maps from our academic source attempt to do.
Oh, really?
Yeah. You can take a specific location, like Seoul or New York or London, put it at the absolute center of a blank map, and mathematically project the great circles extending outward from that one specific point as perfectly straight lines.
Okay, so that solves it. But I'm guessing there's a catch.
The catch is perspective. You
Ah,
can only make it visually perfect from that one specific anchor point. The moment you move your starting point away from Seoul to a different city, the visual distortion comes rushing back.
oh, I see.
This is the classic peeling an orange problem.
Right.
You cannot take the skin of a spherical orange and lay it completely flat on a table without stretching, tearing, or distorting the geometry somewhere.
Yeah, you'd have to rip it.
Exactly. It is mathematically impossible to create a 2D map that perfectly represents 3D spherical distance from every angle.
So we are just permanently stuck with maps that lie to us.
Visually, yes. Which is why modern navigation doesn't rely on human eyes looking at flat maps.
Thank goodness.
We rely on the math.
That brings up a huge question for me, actually. If a human pilot gets confused by a flat map, how do computers and autopilots actually navigate these arching routes without getting lost?
Right.
I mean, if a great circle is just a concept, how do you tell a machine to fly it?
This is where the academic paper gets into the mechanics of modern routing, focusing on a mathematical operation known as SLAIR.
SLAIR.
Yes, that's
I just say it sounds like a gas station coverage, not a navigation tool.
It really does.
Yeah.
But it's vital.
It stands for spherical linear interpolation, right?
Yes.
Now, I know what standard linear interpolation is. Like if I have point A and point B on a graph, the formula just finds the dots directly between them to draw a straight line.
Like that.
So why do we need a spherical version? Like, why not just use standard GPS routing?
Because if you run standard linear interpolation between 2 points on the globe, the math will draw a perfectly straight line between them.
Okay.
But a perfectly straight line between New York and Madrid would require the airplane to tunnel directly through the Earth's crust.
Oh,
Yeah.
because the Earth is curving outward, a true straight line cuts right through the ground.
Exactly. SLRP forces the mathematics to ride the surface of the sphere.
Okay, that makes sense.
It calculates the central angle of that great circle, and then it generates waypoints at equal angular distances along the curve.
So if I'm leaving Seoul, the SLOP formula doesn't just give me the end destination.
Right.
It gives me an exact 3D coordinate when I am, say, 10 degrees away from my departure point.
Yes.
And then another hyperspecific waypoint at 20 degrees and so on, basically building a dotted line along the arch.
This raises an important question about how dependent we are on this invisible math. I mean, SLRP is the backbone of commercial flight paths and global shipping lanes, but it is incredibly vital for the navigation of autonomous drones and UAVs.
Why are drones different than a commercial flight? I mean, don't they both just need directions?
Well, imagine an autonomous delivery drone trying to navigate a long-haul flight across the Pacific Ocean.
Okay.
A drone doesn't have a human pilot looking out a window to orient themselves, and it doesn't look at a flat map monitor.
Right.
If that drone's programming relied on a flat grid calculation, it would calculate a heading, start flying, and immediately begin drifting off course.
Because the ground below it is curving.
Exactly. The physical Earth is constantly curving away from its mathematical expectation.
So it would constantly realize it's in the wrong spot, recalculate, adjust, realize it's wrong again, and adjust again.
And in doing so, it would burn through its battery life fighting the curvature of the Earth. It would likely fail its mission completely. SLRP gives the drone true geometric GPS waypoints in three-dimensional space, which allows it to glide along the Great Circle effortlessly.
Oh, that's amazing.
The machine operates in the reality of the sphere, while we humans are constantly trying to force the world into the illusion of a flat rectangle.
Yeah, we really are. So what does this all mean?
All right.
If we step back from the SLRP formulas, the shrinking onion slices, and the airplane fuel savings, the biggest takeaway from our stack of sources today is a fundamental paradigm shift.
Very much so.
The flat maps hanging in our classrooms and on our phones are, at best, a convenient shorthand. At worst, they are an absolute optical illusion.
Yeah.
If you want to grasp real distance, and if you want to understand the invisible tracks that guide the global economy, you have to let go of the flat grid.
It requires completely rewiring how we visualize space.
Yeah.
And I think there is a final lingering thought here that goes far beyond drone routing or jet fuel.
Cool. That's that.
If our standard 2D maps so heavily distort physical distance, literally tricking our human eyes into thinking the absolute shortest path between two cities is a massive detour, how much has this warped our psychological and geopolitical understanding of the world?
Oh, wow. That is heavy.
We stare at these distorted flat maps our entire lives, And we form deep internal biases about which countries are near to us and which countries are far.
Right.
We view certain nations as incredibly distant, isolated, or fundamentally disconnected from our own region, simply because a map projection invented in the 16th century stretched them out across a piece of paper.
Right. Because they're on the edges of the map, we think they're worlds away.
When in the true, undeniable geometry of the sphere, if you just arched a little bit north, they are practically right next door.
That is wild.
We let a distorted 2D blueprint dictate how we view the physical 3D house we all live in.
We really do.
Yeah.
It just goes to show the next time you look at a perfectly straight line on a map and you think you know exactly how far away something is or how isolated a place might be, you might want to double-check the math.
Def-
Because on a spherical planet, the straightest path is almost always a curve.